Self introduced ಮಾಡ್ಕೊಳ್ಳಿ ಸರ್.
ಯಾವುದು ಸರ್?
ಸೆಲ್ಫ್ ಇಂಟ್ರೊಡ್ಯೂಸ್ ಮಾಡ್ಕೊಳ್ಳಿ.
ಮಾಡ್ಕೋಬೇಕಾ?
ಸೆಲ್ಫ್ ಒಂದು ಕ್ಲಾಸ್ ಮಾಡಿ.
Hello students, this is Professor Sanjay Eligar here. I am from BB College of Engineering and Technology, Hubli. So I am an assistant professor in ENC department over there, and my research interests basically include VLSI. So it's an honor for me to be here to present this course, Analog and Digital Electronics, which is for computer science students. So before I go into this subject, it's always a scenario which happens like, okay, I am a CS student, why should I study this analog subject, why should I study this electronics subject? So well, I can only say that nothing is a single discipline in today's world. So everything that we see, like you can't say, okay, I am only going to be a programmer, I am not going to be a systems engineer. And I can't say that I'll only be a hardware engineer and I'll not be a programmer. So the real world out there requires both the skills for any student which comes out of engineering graduation program. In that context, I urge all the students to take this subject also equally seriously so that you become an overall systems engineer once you go into the industry. Okay, so let me just quickly run through what's the content that you have for this particular course. The course objectives for this course are, this should enable the students to recall and recognize construction and characteristics of JFETs and MOSFETs and differentiate the same with respect to BJTs. As we all know, BJTs would have been studied by you all in the first year of engineering and to some extent also in the +2 programs after your schooling. Next, the objective would be to demonstrate and analyze operational amplifier circuits and their applications. Thirdly, describe, illustrate and analyze combinational logic circuits, simplification of algebraic equations using K-maps and Quine-Mikulski techniques. Moving on, the next 3 objectives of this particular course are, it should enable the students to describe and design decoders, encoders, digital multiplexers, adders and subtractors, binary comparators, latches and master-slave flip-flops. Now all these are basically the blocks that we call as digital blocks. Then describe, design and analyze synchronous and asynchronous sequential circuits. Finally, the course winds up with a mix of analog as well as digital, which we call as mixed signal circuits, and they typically involve the conversion from analog to digital and vice versa. So last objective is to explain and design registers and counters, A to D and D to A converters. So hopefully by the end of this entire course, you should be able to achieve all these objectives, and it will be our endeavor to try to teach you as many concepts as we can and try to learn together as we go along. Now as far as the course modules are concerned, we are going to have these modules as far as the first based on the chapters that you basically have. So what we typically call as the content or syllabus for your particular course. So broadly we can call these chapters as FETs, basic gates, data processing circuits, flip-flops, counters. The textbooks that has been prescribed by VTU are Anil Maini and Varsha Agarwal, which is Electronic Devices and Circuits by Wiley publication, from which we are going to take majority of the content as far as the first session is concerned, which I will be handling. Next, there is a Donald Leach and Malvino Saha, Digital Principles and Applications, which is a Tata McGraw-Hill edition. So moving on to the first module which will be handled, this we are going to split it into 7 sessions, which is essentially actually a 10-hour delivery program. So we are squeezing it into 7 hours to cover the most important aspects. The remaining 3 hours we expect the students to go back and hone their skills further and build on these concepts by solving additional problems or by referring the reference books. So the 7 sessions which have been identified are FETs, which include JFET and enhancements MOSFET, then depletion MOSFETs, differences between JFETs and MOSFETs, and biasing MOSFETs, which is a large topic, dividing it into 2 sessions. Then moving on, we have FET applications and CMOS devices. The last 3 sessions would be something called as wave shaping circuits, where we will be discussing with the IC wave shaping circuits and not the discrete device circuits. Then we introduce you to the operational amplifier and some of the applications which use this op amps, which go on till active filters, amplifiers, and finally to voltage to convert, current converter and current to voltage converter. So again, I welcome you all to this particular session. So let us get started by doing this first session, which is on field effect transistors. Essentially, we will be covering JFETs and enhancement MOSFETs. Now, before we start with this particular session, let us try to see what's the learning outcome that we expect out of this session. Now, upon successful completion of this session, the students should be able to acquire the knowledge of JFETs and MOSFETs. The student should also be able to analyze the performance of JFETs and enhancement MOSFETs. So with these outcomes in mind, let us start with the first session. Now, we all would have studied the various devices starting from a schooling into the college and also in the first year of engineering. We have been introduced to a device called as a PN junction diode to start with, and then we were introduced to something called as BJTs, which we call as bipolar junction transistors. Now, how are these two going to vary? Now, since we have already studied BJT, why is it that we should study FETs? So let us start this topic by giving a context as to why we have to move on to FETs. Was not studying BJT good enough? Why should I study one more device? That is a usual grouse of many students. But as we know, technology keeps advancing, always for betterment. So let us see the main comparisons or advantages vis-a-vis BJTs and FETs. Now, primarily BJTs are current control devices. That typically we say collector current and base current. We all must remember the equation IC is equal to beta times IB. That's basically the current amplification which is happening. So you control the base current. By controlling the base current, you can control the output load current. Whereas in FETs, it is going to be a voltage control device, wherein we apply the control voltage at the gate, while the output current can be modified or adjusted accordingly. That's why we call it as a voltage control device. And then moving on to the type of charge carriers which are used. Now, as we all know, right from PN junction diode, it consists of 2 types of charge carriers. So can you guess what are those 2 charge carriers? Well, you said it right. Yeah, the 2 charge carriers are electrons and holes. So we call that as bipolar device. So if it is a NPN transistor, we call electrons as a majority carriers, while we call holes as the minority carriers. If it is a PNP transistor, we call it holes as the majority carriers and electrons as minority carriers. That means both these charge carriers contribute to the overall current. Whereas in FET, it is just one type of charge carrier which operates or causes amplification or as a FET. So it can either be of N type where only electrons are the charge carriers, or it can only be of P type where only holes are the charge carriers. So that's another major difference between these two. Then as far as the third one is the most important part, as far as the low input impedance is concerned for BJTs, that becomes a problem. We need to have the input impedance for any device when it is used as an amplifier as high as possible. Now, why is it so? Suppose let us say I am having a signal which is driving at the input of this device. Now, if the device has a very low input impedance, it has a tendency to load the source. In the sense, the source will get loaded. If on the other hand I have a very high input impedance, I will not be loading the source. That's a good advantage to have. So wherever we have low noise amplifiers, FETs are the best choice as compared to BJTs. Plus, then coming on to fabrication or what we call as construction, it's much complex when you're doing in case of a BJT, whereas in case of an FET, the fabrication is much simpler. It involves much less number of steps. By fabrication, what do you mean? We keep saying that it is a NPN transistor. So we need to have an N-type doping, a P-type doping and another N-type doping as a base, emitter and collector. So that is called as fabrication. We have to do it in various steps sequentially, one after the other. So which is typically more complex in a BJT as opposed to that in a FETs. So that's an advantage we have for FET fabrication. But Is FET good everywhere? No, it has a slight drawback in terms of the gain that a single stage device can provide. BJT has a much larger gain as compared to FET. So that's the only sore point as far as FETs are concerned. But nowadays even that is also taken care of. We have something called as bi-CMOS devices where it uses BJTs at the output stage while it uses FETs in the processing stage. So thereby I can have the best of both worlds. And finally, there is also one more thing. FETs you need to handle very carefully because static electricity in your fingertips can damage the chips or the ICs or the devices. So that's not the case with BJTs. So net we can say 4:2 when it comes to FETs and BJTs, but looking at the cost, looking at the compactness and the volume, the shrinkage FETs allows you to do in a chip, FETs has far overtaken BJTs. Okay, so let's move on then and try to see what these FETs are all about. Now, as we kept on saying FETs, so FET is an acronym for, like JFET is an acronym for Junction Field Effect Transistors. So how is construction or the way in which this particular JFET looks like? Now here we are showing you two such devices. As I said, it's a unipolar device. So we're going to have a N-type JFET and we're going to have a P-type JFET. So accordingly, you can see the construction here. In this particular slide, we have a huge piece of N-type material onto which we have doped two P-type junctions. Okay, so bear in mind, so this particular thing is now a 3-terminal device wherein we call one as a drain, one as a source and one as a gate. Now we are trying to show the gate as connected to each other, but what actually is it that we are showing here is a cut section of this particular device. So it appears as though we have gate on one end, but okay, fine. So the 3 terminals will now be called as drain, the source and the gate. Likewise, if you want to have a P-channel JFET, then we're going to have a P semiconductor onto which you dope two regions at gate which are of N-type. Now to understand the behavior of this JFET, we need to revisit one concept as far as semiconductor devices is concerned. So that concept is a concept of what we call as the depletion region. So can anyone tell what a depletion region is all about? Okay, so let me just try to move to the board here and try to ask you some questions. So basically we all know that we have what we call as a PN junction diode. So this would be the schematic of a PN junction diode. We call this as a P-type and we call this as a N-type. But then how does it look as far as the construction is concerned? So we are going to have a P-type material on one side and we're going to have a N-type material on the other side. Now what happens is, the moment you have a P-type on one side, the moment you have an N-type on the other side, what do you have in the middle here? Is there going to be an abrupt transition from P-type to N-type? No, right? We're going to have some region in between these two. Now that region we call as depletion region. You're right. So what does a depletion region mean? Depletion region means that particular region is devoid of any charge carriers. We have majority of holes on this side and we have majority of electrons on this side, whereas we do have minority electrons here and minority holes here. Now these holes, they try to move from this side to this side, thereby leaving what we call as a negative ion band, because I am going to lose a positive charge from the P side to the N side. Likewise, an electron which moves from this side to that side leaves behind a positive fixed ion. So the entire region between the P and N type now becomes devoid of any of the charge carriers, which we call as the depletion region, meaning that region is depleted of any charge carriers. So let's go back then. That means what, have I given any potential here? No, just by merely having a P-type diffusion on one side, an N-type diffusion on the other side, I am going to have a depletion region. Now this width of the depletion region can be altered if I apply what we call as an external bias. Now we have something called as a forward bias and we have something called as a reverse bias. Now, can someone tell me what would be a forward bias for a PN junction, right? So, we are going to connect the P type to the positive of the battery, and we are going to connect the N type to the negative of the battery. So, this we call as forward bias. If you forward bias a junction, the width of the depletion region would reduce, while if we do the reverse of it, in the sense, if I am going to replace this voltage source by an opposite one, like connecting the P type to negative and connecting the N type to positive. So, what is this happening now? The positive here will attract all the electrons from this side, and the negative here would attract all the holes from this side. So, what would happen? You would have the widening of the depletion region. So, this reverse bias diode, we know it increases the width of depletion region. Now, this is one concept which we need to apply in understanding the behavior of a JFET. If we do not know that by applying a reverse bias the width of depletion region increases, then we can't understand the operation. Increasing the voltage further, it goes on widening, but to what extent? Beyond a point, we have something called as breakdown. So, what breakdown? I am giving you a hint here. Yes, it is called as an avalanche breakdown. Okay. Once you exceed the reverse voltage beyond a point, the diode simply breaks, and you no longer have a junction called PN junction. We just have one full piece of semiconductor material. So, let us move back to the JFET now and try to understand how we can apply this concept to understanding the behavior of JFET. Before we move on, just the symbol, like how, just like we have a symbol for the diode here, we also have a symbol for JFET, if you can see it in the slide here. Now, N-type JFET, you can see the only difference is it has the arrow mark pointing inside, whereas a P-type has the arrow mark pointing outside. Apart from that, there is no difference as far as symbol is concerned, very similar to what we have in NPN and a PNP. Whereas in BJTs, the arrow mark, do you remember where the arrow mark was in a BJT? Yes, right, it was on the emitter, whereas in this case, the arrow mark is shown on the gate terminal. Okay. So, arrow mark going inside is a N JFET, going outside from the gate is a P-type JFET. Now, how do we see the operation of this JFET? When we see operation of JFET, all I have to do is control the voltage and see the current, because at the end of the day, we kept on saying that FET is a voltage control device. So, what to do next then? Apply a voltage and see how the current can be modulated or how the current can change. For that, we need to have a circuit configuration. So, the circuit configuration for finding out those characteristics is given here. Initially, we do not apply any gate to source voltage, in the sense we short both gate as well as source, which ensures that we have VGS as 0. And then we are going to apply a voltage here between drain and source. Okay. So, this is the schematic connection and this is how the actual connection looks like. Now, immediately after applying the positive voltage to the drain terminal and the negative to the source terminal, you can see the depletion region now changing its pattern. Let me go back to the previous two slides and see what was happening there when it was not biased. When it was not biased, you can see here the depletion regions were of constant width. See here the same way. It is very similar to an unbiased PN junction. Okay. Now, the moment you start applying the bias, what is the applied bias here now? I am connecting the the N type here to positive. Just like in case of a diode, if you connect the N type to the positive, it's a reverse bias. While the P type, if you can see here, the P type is, you can see the connections here, the P type is connected to the negative. So, P to negative and positive to the N type ensures that it is now a reverse biased junction. Not only that, the moment you have a reverse bias junction, you can see the depletion region width changing. Now, you may ask the question, why is the width larger here than here? We will come to that a bit later, But before that, let us try to understand how the current flows with the voltage being applied. So for that, let us try the help of animation here, and it will help us understand these concepts in a much more simpler fashion. So this is the case now. I have a MOSFET here, wherein my VGS is 0 volts and I am not applying any drain to source voltage also. So just like we saw in the previous slide, the orange one is the depletion width. There is hardly any depletion region here. So, and there is no current also in this channel. Now we call this region in between the drain and source as the channel. Now let us see, I will slowly increase the drain to source voltage. From 0 volts, I will move on to 1 volt. So what you can see now, the positive of it attracts the electrons, right? Because electrons being negatively charged, they get attracted towards the positive of the pole. So what we have is the flow of electrons from the source side to the drain side. So if the electrons flow from source to drain, where does the conventional current flow? Now as per the basics of physics, we know that the direction of flow of conventional current is always opposite to the flow of electron current. So if we say that the current is, electrons are flowing from source to drain, then we can say the current is flowing from drain to source. Do not get confused here, it's a convention that has been going on. So if electrons flowing from source to drain, current is flowing from drain to source. Now you can see the rate at which these electrons are moving from source to drain. Now can I increase this rate at which they are moving? Let's see by increasing the voltage a bit more further. Also, I urge you to observe this depletion region width very carefully. Okay, so now I'm moving from 1 volt, now I take it to 2 volts. So what you can see now, current is started increasing. Why? Because the applied voltage creates a larger potential difference. Larger the potential difference, larger is going to be the rate at which electrons flow, and hence more current. Okay. So does that mean it will go on increasing? Let us see. So let me now take it to something called as 3 volts, and now you see there something happening, right? Increasing it further, right? Now this is the very interesting part. What is actually happening here? The width of the depletion region on the drain side is more as compared to the width at the source side. Why this happens? Any guesses? Okay, a very simple way to explain this concept. If current is flowing from drain to source, what does that mean? Drain is at a higher potential than source. So that means what? This region of the P type is experiencing a larger reverse bias as opposed to the source region, which is not having, because it's at ground, so essentially no bias there. So once this happens, as we studied in the context of a PN junction diode, larger the reverse bias, larger is going to be the depletion width. Now as you go on increasing the voltage, you reach a point what we call as a pinch off point, wherein these two junctions, they simply touch each other, and after that we do not have any current flowing. So this entire thing now can be seen from this point. So now I urge you to look at the graph here on the graph on the left side. So what is happening? The current is slowly increasing from 0 to 20 milliamperes, and then it is saturating at some point. Okay, so I'll again redo this slide, but now I expect you to look at the graph there and see how the behavior works. So you can see the green line there, it starts from 0. Okay, now this region we call as a ohmic region. Why ohmic region? Because increase in the applied voltage is causing a increase in the current. Okay, but beyond a point, what we call as the pinch off point. Now what is this pinch off point? Pinch off point means the depletion region at the drain end touches each other. Once this happens, no matter how much we increase the drain voltage, the current remains constant. So this we call as the saturation region. Now let's go back to our slide and see what actually happens at pinch off. Okay. So this is the same curve which we showed there for VGS equal to 0. Now what if VGS is made either larger than 0 or it is made less than 0. Let us see what will happen in that case. Okay, so let's go back to the diagram here. Now I am increasing the VGS further. So what will happen now? So you can see there the current is reducing. Okay, I am trying to show you the pinch off point now. See there, this is what I mean by the pinch off point, right? It totally touches each other and you no longer have any current flowing if VGS is increased much more. Now if you have observed, I am giving a negative gate to source voltage. So giving a negative gate to source voltage further reverse biases this junction, okay, and causes an increase in the depletion width. So you can see the curve on the left side also, the bar is now moving downwards. Okay, so we're going to have different sets of curves. The blue one is a 1 now for VGS equal to minus 2 volts. I can increase the negative voltage, the current goes on reducing. So what does that mean now? A larger negative gate voltage increases the depletion width further, and you can see there the current also reduces to a lot extent. So this way I can modulate the current which flows in the channel. Okay, I'll show you how I'm doing a gate control. Okay, that's the idea. So 0 voltage at the gate, the current is the highest. Okay, I can see there. You can see that the current is flowing pretty fast. Now I go on giving a negative bias. See, the currents are starting to reduce. The number of electrons you are able to see, they are reducing. So what does that basically mean? I am able to modulate the current in the channel by applying or controlling the gate to source voltage. This is what we call as voltage controlled device. Applying a voltage at the gate, modulating the current at the output. So this would clear all the doubts you have as to how this particular thing is operating. Okay, so let's move on then. The same thing that we are trying to show here. Earlier VGS was 0, now we are giving a negative voltage. So how does it become a further reverse bias? Okay, it was a P-type if you remember. You had N-type drain, N-type source, and you had a P-type gate. So a P-type gate connected to the negative of VGG. So that means it is a reverse bias again. So adding additional reverse bias at the gate causes the depletion width to increase further and thereby reduce the current even further. This is the overall set of curves for various values of VGS. Now what happens if I go on increasing the reverse bias further, okay, or I go on increasing the VDS further? So as you can see in these curves, just like you have an avalanche breakdown in a PN junction, here also we're going to have an avalanche breakdown. Okay, so as you can see here, for very large gate voltages, you go into a breakdown region wherein the current suddenly shoots up. Why the current shoots up? You no longer have a junction, it is just a piece of semiconductor material with very low resistance, so current shoots up from milliamperes to even amperes and it actually destroys the JFET. You can no longer recover from that situation once you go into a breakdown region. Now how do we classify these regions here? Now we have something called as the ohmic region and we have something called as a saturation region. Now why do we call ohmic region? It's a very straightforward concept. What does an ohm relation mean? The voltage is directly proportional to R. So larger the voltage, larger would be the resistance here. And then we have beyond the pinch off point, we're going to have what we call as a saturation region. Now there is an equation which governs this particular resistance. So if I'm operating in the ohmic region, my equation for resistance is given by this. RD is equal to R naught divided by 1 minus VGS upon VP whole square, where VP is the voltage at which pinch off occurs, the drain to source voltage at which pinch off occurs. Now if you want to increase the resistance, what should you possibly do? Should you increase the VGS or reduce the VGS? Can you just answer that by means of a question? By looking at the graph or looking at the equation? Both are possible. Let us start with the equation first. So increasing VGS, what would happen? My denominator would reduce. So if the denominator is reducing, okay, so then the overall figure is going to increase. So larger the value of VGS, larger is going to be what? Fine. So let us go back to the board here and try to see what do you mean by resistance and what do you mean by the slope. Okay, I'll just rub this. Okay, so Ohm's law says V is proportional to I. Now this proportionality constant is what we call as resistance. So V is equal to R into I. If I were to draw the graph of this, what would happen? Okay, I will give on the x-axis if I give V, on the y-axis if I give I, then this would be the nature of the graph. At V equal to 0, I would also be 0. Now what is this slope now? This slope is given by what? If I can call this as delta I, okay, delta I, and if I can call this as delta V, then what is I upon V here? I upon V would be actually 1 upon R. Yes or no? Okay, because I am taking V here, R goes here. So this slope is actually giving me the inverse of the resistance. Okay. Likewise, now we go back to the slide here, and if you can see, each of these waveforms over here, now they are going to have different sets of slopes. Okay. This is the one which has a much lesser slope as compared to this one which has a higher slope. So higher the slope means what? We already seen slope is inverse of resistance. So higher the slope, lesser the resistance. So this way also you can analyze this resistance. Once we know the ohmic region, then can we define some equation for the saturation region? Okay. And by the way, what is this R naught here? R naught would be the value of the resistance at VGS equal to 0. Okay. Now once it is in the saturation region, what is the current that we are looking at? The current would be ID is equal to IDSS 1 minus VGS upon VP square. Again, what is this IDSS? Now IDSS is the saturation current for VGS equal to 0. Thereafter, for any larger value, when I say larger value, larger negative value of VGS, the current goes on reducing further, and this equation is a famous Shockley equation, in the sense a square law equation, which is a very powerful analysis which helped these FETs and even MOSFETs as we go down being used in many of the communication devices like tuners and all. The reason being, if you have a square law device, it is going to produce the even number of harmonics so that your noise is going to be reduced. Whereas in BJT, it is not a square law, it is a direct law, like IC is equal to beta into IB. So there you have more noise, whereas in FET is going to have much lesser noise. That's the reason we are using FETs in low noise amplifiers. Now moving on, the previous characteristics we called them as the output characteristics. Why output? Because current is the output, okay, and VDS is also the output. So an output voltage versus output current is called as an output characteristics. Now we can also plot what we call as the transfer characteristics. What does transfer mean? In to out. Now what is the input in our case? The input in our case is VGS, and the output continues to be the drain current. So you can do a calculation from the graph also, or you can also use the graphical method, or you can also use the equations to establish a relation between VGS and ID. It's an exponential relations which we are having. So you can see here, the current is maximum when VGS is 0. As you go on applying a negative gate to source voltage, the current goes on reducing down, and this is how the graph would look like. So this we call as the transfer characteristics. Okay. So far what we have done is all about N-type JFET, or what we call as N-channel JFET. Now we also saw that we also have a P-channel JFET. So what would be the difference between these two? If we were to analyze, everything would look the same, only the polarities would get changed. If VDS would be positive there, here VDS would become negative. If ID was positive there, here ID would become negative. So if you can see here, we have just shown just one shot of the curves wherein you can see the entire output characteristics looking the same, but you need to observe what is there on the x-axis. It is negative value of VDS and negative value of ID. So rest all analysis remains the same. So once you analyze the N-channel JFET, the P-channel JFET is got to be the same, with the exception that all the voltages will have a reverse polarity, all the currents will also have the reverse polarity. Okay, so that's it as far as the JFETs were concerned. We have seen the N-channel JFET in detail. Now we just showing a snapshot of what a P-channel JFET would look like. Now moving on to another type of device which we call as MOSFET, very famous, very popular and widely used device beyond BJTs and JFETs also. Now what does MOSFET stands for? As we are showing there, it is metal oxide field effect transistor. It is also a voltage control device, but we have an insulator in between the gate and the channel, which we'll see in the next few slides. Let us briefly give you a snapshot as to what is it that we're going to cover in these MOSFETs. So we have two types of MOSFETs, not talking about the N type or P type, the two varieties of MOSFETs which we call as enhancement MOSFETs and depletion MOSFETs. And then we go on to see the difference between the JFETs and MOSFETs, and eventually we are going to do the biasing of MOSFETs. Okay. So this is a typical construction of a enhancement type MOSFET. Now before I keep using this word enhancement and depletion, let me quickly tell you what's the difference between these two. So if you can observe the construction here, we have again 3 terminals, but the difference is we also have a 4th terminal which we now call as a substrate. So essentially JFET were 3 terminal devices, whereas MOSFETs are 4 terminal devices. The 3 terminals remain the same: the source, the gate, the drain, plus the substrate. So the construction here, you can see here, these are the drain and the source regions, and you have a substrate which is of P type. So there is no connection between source and drain, whereas in JFET there was always a channel where the current could pass. In this case there is no channel which is present. Okay, that means what? How does it work then? It only works when you apply a gate voltage. Once you apply a positive gate voltage here, a channel is formed. That's why we call it as an enhancement type MOSFET. Whereas in a depletion type MOSFET, even though if you don't apply any gate, there would already be a channel between the drain and a source, alike, just like a JFET sort of a thing. Okay, the major difference is, you can see here, this is the gate terminal. It is no longer connected directly to the substrate or the P-type terminal. We have a oxide or an insulator in between, which is typically called as a silicon dioxide as an insulator, the SiO2 that we have shown here. Okay, and how are these contacts taken from the semiconductors? By means of ohmic contacts or metal contacts, as the case may be. So what's the difference between an N-type enhancement and a P-type enhancement? The only difference is we have highly doped source and drain regions of N-type, where as a P-type as a substrate, whereas in a P enhancement we have a highly doped drain and source regions over a N-type substrate. Okay, so that's the difference. So let's move on and tell the symbol of it and then move on to the operation of it. So it may look a slightly tricky symbol here, but you don't have to worry. The only difference here is you can also use this 4-channel MOSFET as a 3-channel. I mean, sorry, a 4-pin MOSFET as a 3-pin MOSFET. Now the 4 pins are gate, source, drain and the substrate. Now if you don't want to use the 4th terminal, you can always short it to the source, which is usually done over here like this. Again, if it is N-type, the arrow mark is going inside. If it is a P-type, the arrow mark is going outside. Very similar to what is a convention for JFETs. The another point which you have to note here is the line between the drain and source is a dotted line. It is not by mistake, it is by design. In the sense, we are trying to depict through this symbol that the drain and source are generally not electrically connected when there is no gate voltage applied. Only upon application of the gate voltage will there be a connection between drain and. That's why we show it as a dotted line, means there is no connection between drain and source. So this is N-type and this is a P-type. Now let's see the operation of a MOSFET. Again, we will try to see or use the benefit of simulation for this one. Okay. So this is a particular animation that we are trying to do for. Okay. So we have a source region here and we have a drain region here, plus we also have a bulk here which is of P type, and you're going to have the N type source and drain plus the gate. Initially, I do not connect any voltage between gate and source. You can see here gate and source. I'm making gate and source as 0. Likewise, I'm not going to connect any voltage between drain and source. That means I'm going to keep VDS as 0. So if we see the graph here, there is no current flowing between drain and source, and we say the device is in cutoff state. Now how do you turn the device on? To turn the device on, we need to have a channel between drain and source. When do we have the channel? We need to apply a gate voltage which is larger than a voltage which we call as threshold voltage. So let's try and do that here by giving a larger gate voltage. The moment I give a larger gate voltage, you can see what happens is the electrons which were minority carriers in the P substrate, they are moving up towards the interface. Now can they go and reach the gate? No, they can't reach the gate. Why? Because you have an insulator in between the gate and the P-type substrate. But the electrons, they go and they get accumulated below the surface, just like in case of a capacitor, right? What do you have in a capacitor? You can have the charges come and sit on the plates, but they can't cross from one plate to the another. So go on increasing the gate voltage further. Now you can see the channel has been formed. I'll increase the voltage here. You can see the depth of this channel goes on increasing. That means more number of electrons are coming beneath the channel. So does that mean I have a current now? I should have, right? I have a gate here which has caused me a channel to be formed. I have a connection between drain and source. So why should not any current be flowing? The very simple fact, for any current to flow between drain and source, you need to have a potential difference between drain and source. Right now, what is the potential difference? 0 volts. So if the voltage between drain and source is 0, you will not have any current flowing from drain to source. So let's sweep these electrons from source by increasing the drain voltage. And simultaneously, let's also observe what happens on the curve. Okay. So let me make my VGS as VDS as 1 volts, my VGS is already 5 volts. So as you can see here, we already have a current now which is flowing from source to the drain. I'll increase the drain to source voltage further. So you can see here the drain voltage is increased. You can observe the simulation here. Pause ಆಗಿರುತ್ತಲ್ಲ. Okay, so there you go then. So increasing the VDS further is going to cause an increase in VGS. To what extent? So let us go back from 0. For VDS equal to 1 volt, there is some amount of current here as shown. Increase it further. Also observe the channel here. The depth of the channel is becoming smaller here. This is again very similar to what we called as a pinch off effect in JFET. Okay, the reverse bias at the drain end is much larger as compared to the source end. So the channel depth here is reduced. Increase the drain voltage further and I reach what I call as a pinch off. Pinch off means there is no longer any channel at the drain end. So beyond this point, no matter whatever is the increase in the VDS, it will not cause any increase in the current. Okay, so that is seen here. I am increasing VDS beyond, no increase in the current whatsoever beyond the pinch off. So likewise, what happens if I increase the VGS further? So from 5 volts, let me take it to 10 volts. What will happen? Definitely much larger current. Why? Because the channel width is much longer. So this is how a MOSFET operates. In the sense, by controlling the gate voltage, I can modulate the drain current. The drain current is also depending on the drain to source voltage, but only up to a point called as a pinch off. Beyond pinch off, I go into saturation, and before pinch off, I go into what we call as a ohmic region or the triode region. And when VGS is less than the threshold voltage, I no longer have any channel, and so I call that as a cutoff region. So this was what the operation of N-channel enhancement MOSFET was. Okay. So this is again depicting the pinch off condition, wherein the depletion region is much larger at the drain end, thereby it is causing the depth of the channel to become 0 at drain end. This is called as a pinch off condition, beyond which it enters saturation. Just like we have output characteristics curves, means what? Output voltage VDS versus output current ID for JFET. Likewise also we have output characteristics here. The curves are pretty much similar. Okay. So for increasing value of VGS, you're going to have much larger current. Whereas in JFET, what was happening? The current was the highest at VGS equal to 0, and for a negative VGS, it was reducing. We also have something called as a transfer characteristics. Again, what does transfer mean? Output current versus input voltage. This is what depicts the voltage controlled device behavior. I am able to change the voltage and then get a change in the current. So we can now sum up the entire session here. What is it that we have done in this entire session? We started by seeing the construction and operation of the junction field effect transistor, and then we moved on to the enhancement type metal oxide semiconductor field effect transistors, which we call as the MOSFETs. Then we studied the output curve as well as the transfer curve for both the devices. Before we wind up, can we just have one or two questions so that we can understand whether we are being able to understand this fully. So I'll just float one or two questions. So let us see whether you all will be able to answer this. Now my first question would be on, if you can move to the board, my first question would be on JFETs. Okay. So how many terminals does a JFET have? Okay. The JFET is having 3 terminals, right? So what are those 3 terminals? Those are the gate, the drain, and the source. Now how about MOSFET? Is MOSFET also having only 3 terminals? No, right? It has 4 terminals. Okay, the answer is right. So MOSFETs are going to have 4 terminals, which are gate, drain, source, plus we also have something called as a substrate. Okay. So the next question would be, in a JFET, when is the current the highest? I have 2 scenarios wherein in the first case I have my VGS equal to 0 volts, and in the second scenario I am going to have VGS equal to minus 2 volts. So when do you think the current would be the highest? Right. So the current in JFET is highest when VGS is 0. Thereafter it sort of depletes the channel, and so the current reduces. Whereas in case of MOSFETs, let me give a condition for N channel where VGS is 0 volts and again when VGS is 2 volts. So in which case the current is higher? It's exactly the opposite, right? So in VGS, in 0, there is essentially no current flowing, and even at 2 volt, if it is the threshold voltage, again no current, right? So if our answer was you have more current at VGS equal to 2, you may again be wrong. It depends on if this is the VT, the threshold voltage, then you will not have any current. So only if the gate voltage is larger than the threshold voltage, you will have the higher current. So larger the value of gate to source voltage, larger would be current in a MOSFET. So with that, we'll just sort of sum up this entire thing. So urge students to delve deeper into these 2 devices, the JFET and the enhancement MOSFET. In the next session, we'll come to the depletion MOSFETs and we'll take on from there. Okay. Thank you one and all.